Hello students, let us continue our discussion on motion in a straight line. In the last session, we were discussing about speed and velocity. And in speed, after discussing the definition, formula, unit and the dimension of speed, and also about the nature of the quantity, like whether it is scalar or vector, we went to discuss about different types of speeds: instantaneous speed, average speed and uniform speeds. We discussed about all of them, and similarly we discussed everything for velocity. Now to sum them up, today I want to give you the differences between distance and displacement and the differences between speed and velocity, because for the board examination this is a very important question. Okay, so let me give you the differences between distance and displacement. Okay, instead of distance they can also give you as path length, right? Distance and path length are one and the same. And displacement, you need to memorize at least 3 differences between distance and displacement. One of the difference, the first one, is as follows. Very simple. You always take the definition itself as the first difference of the quantities, of the factors chosen. So what is the definition of distance? Distance is defined as the total length or the total length of the path, the total length of the path traveled by the body, right? So this is what is distance, definition of distance. Similarly, definition of displacement itself will be the first difference. So what is displacement? Displacement is the shortest length between initial and final position of the body, right? So this is the first difference between distance and displacement. I have explained all of them. They are easy. You understood them. It is just the pattern which is important to observe now, the differences. Next, what kind of quantity is distance? See, all the quantities can be categorized into either scalars or vectors. And distance is a scalar quantity, displacement is a vector quantity, right? So distance is a scalar quantity and displacement is a vector quantity, right? Vector means one which has direction. Scalar means one which does not have any direction. So that is the second difference, very easy. Now, what about the third? The third difference is, see, once the motion has happened, distance can never be 0, but displacement can be 0, right? Similarly, displacement can be both positive and negative, but distance is always positive, right? We have discussed about it. So, distance is always positive, right? Displacement can be both positive, negative, positive and negative. So this is the third difference. And fourth is distance cannot be zero after the motion or after the motion is fine. So once the motion has happened, distance cannot be zero. But displacement can be zero after the motion, right? Because if the body starts from a point, goes certain distance and comes back to the same point, then the displacement is zero, because initial point and the final point both are the same. So displacement can be zero after the motion. Okay, these are the differences between distance and displacement. Now, the same way, we are going to discuss the differences between speed and velocity. Many of the factors remains the same. Many of the differences here remains the same. Like distance is a scalar quantity, instead of distance, we will put speed, and instead of displacement here, we will replace it by velocity. So now, the differences that we are going to take is speed and velocity. Okay, this is another important question. What are the differences between speed and velocity? Okay. See, these three differences, they are same, only the first difference changes. So now it is the difference between speed and velocity. How do we define speed? Speed is the rate of change of distance, right, with respect to time. So rate of change of distance with respect to time is speed. When it comes to velocity, rate of change of displacement, right? Rate of change of displacement with respect to time is velocity. Now, wherever you had speed or wherever you had a distance, you just put them as speed. So speed is a scalar quantity, yes. Velocity is a vector. Yeah. Speed is a scalar quantity, velocity is a vector quantity. And speed is always positive. Velocity can be both positive and negative. Fourth difference is speed can be zero or cannot be zero. Speed cannot be zero after the motion. See here, this is not simply the speed, it's the average speed which we should consider, because instantaneous speed can be zero after the motion, right? But average speed cannot be zero after the motion. Average speed cannot be zero after the motion, and here average velocity can be zero after the motion, right? When the body comes back to the same position, displacement is zero. When the displacement is zero, velocity will also be zero. Okay, so these are the four differences between speed and velocity. Now, difference between distance and displacement, difference between speed and velocity. These two are important questions which you should learn. which is generally asked repeatedly in the board examination. Now let us continue our discussion for the next topic. So dear students, the next topic in motion in straight line is as follows. So say you have point A and point B, and from point a body starts from rest, okay, then goes with a good amount of speed, okay, increasing speed, and suddenly decreases its speed, okay, decreases speed after certain point and comes to zero at certain point, okay. Here increasing speed, decreasing speed, it rests at certain point, okay, comes to rest at certain point, and once again it starts to increase its speed and reaches B, okay. This is the variation that is happening in the speed or velocity of the body while it is traveling from A to B. Now some other body again starts from starts from A and ends its motion at B. This time it goes with same speed from which with which it starts from A. Okay, it starts from A with certain speed, and it maintains the same speed throughout the journey and come to the point B. Now, if you uh, take the average velocities for both the motion, the average velocity for both the motion for this example appears to be equal. What is average velocity? Total displacement by total time taken. Now let me give the details of the motion. Say body A, first body starts its motion from A, say at 10:15, okay, and at 10:20 it till 10:20 it increases its speed, and at 10:22 it comes to rest, and finally at 10:25 it reaches B. Okay. Now the second body starts its motion say at 10:15 itself, but it maintains the same speed and reaches B at 10:25. So for these two motions, when we compare the motions, the average velocity for both the motion is same, isn't it? The average velocity for both the motion is same because average velocity is total displacement by total time taken. Displacement is same for both the bodies. The time taken is also same for both the bodies, isn't it? It is 10 minutes exactly for both the bodies. So when you have this kind of situation where displacement is same, time taken is same, average velocity is same, we need one more factor which can give us the details or the difference of these two motions, right? We need something which can say this motion is different from this motion, okay. So to do so, to differentiate or to make out the difference between these kind of motion, we will now introduce a new factor which is called acceleration, okay. So the new factor that I am going to introduce now is called acceleration, okay. It is also spelled as acceleration, okay. Acceleration, both are fine. The symbol used to represent acceleration is small a, okay. So what is this acceleration? See, you might have heard of accelerator in every vehicle, right? When you take bike, you turn the accelerator, the bike's speed increases, right? The same way in the cars, you put you pedal on the you just press the accelerator, then the speed of the car increases. So acceleration is something which is related to change in speed of the body. In particular, when we consider the daily life examples, when I say acceleration is happening, it means that the speed is increasing, right? The body is accelerating, which means the speed of the body is increasing. That is what the general meaning or general understanding of acceleration is. But let us understand acceleration uh, after its definition now. How do we define acceleration? Acceleration is defined as follows. Okay, acceleration is defined as the rate of change of. Uh, are you feeling like I have seen this before? Yes, you have. How do we define velocity? Velocity is defined as rate of change of displacement with respect to time, right? In the same way, acceleration is defined as rate of change of velocity, okay? Rate of change of velocity with respect to time. So this is how we define acceleration. Now, what is the formula for acceleration? Okay, acceleration is A is equal to, see, whenever I say rate of change of velocity, okay, rate of means there is some factor in the numerator and in the denominator we have change rate of in the with respect to time, okay, rate of with respect to time, which means when I say rate of, there is something, the time, the factor time is always present in the denominator of the formula. Okay, when I say rate of, then t must come in the denominator, keep that in mind. Next, rate of change of velocity. Change of velocity is delta v, right? So instead of simply taking this as t, we can also put this as delta t. See, what is the difference between simply t and delta t? When I say simply t, I have such a stopwatch that as and when the motion begins, I start the stopwatch, and when the motion ends, I stop the stopwatch. Then that is simply t, the total time taken for the motion. And okay, for the same motion, if I do not have a stopwatch, I just need to note the time in the regular watch. Then once the body enters or once the motion starts, we note the time, say 10, okay, 10 hours, 10 seconds, 10 minutes, 10 o'clock, 10 minutes. Then when the motion ends, we once again look at the time, say 10:15. Then what is the time taken for the motion? It is delta t, change in time, 10:15 minus 10:10, which is 5 minutes, right? If I have a stopwatch, it is simply t. If I do not have, then it is delta t. Don't need to bother about those things. It is the same, okay? Delta t and t are actually the same, but that is how they differ depending on the situation. Just keep that in mind. Okay, so acceleration is delta v by delta t. Okay, so what is delta v? Delta v is change in velocity, right? So change in velocity means some final velocity minus some initial velocity, right? So let me take the final velocity as v, okay, small v itself, minus initial velocity as u, okay, some final velocity minus initial velocity u, v minus u, final velocity minus initial velocity by time taken t. Okay, this is what is the formula that we will make use of for discussing problems on acceleration. Okay, a is equal to v minus u by t. These two are the same formula. This is general one, this is the specific one. Final velocity minus initial velocity by time is acceleration. Okay, both formula are valid. Now Uh, what is the unit or SI unit of acceleration? SI unit of acceleration is, see, velocity is in the numerator, which has the unit meter per second, and in the denominator you again have second. So that SI unit, keeping them together, see, meter per second for velocity, okay, by simply second for time, right? So the SI unit of acceleration is meter per second squared, okay, meter per second squared. Meter per second squared is the SI unit of acceleration. And how about dimension of acceleration? Dimension of acceleration is meter L1 per second square t minus 2. Okay, so this is what is the dimension of acceleration. Clear with this? SI unit and dimension, and this is what is everything about acceleration. Now, what kind of quantity is acceleration? Acceleration, see, here you have velocity, okay, rate of change of velocity with respect to time, not rate of change of speed with respect to time, okay, it is rate of change of velocity with respect to time. So since we have velocity there, rate of change of velocity, so velocity is a vector quantity, and hence acceleration will also be a vector quantity, okay. Acceleration is a vector quantity, okay, very simple. This is about acceleration. Now, as similar to what we had in velocity, the different kinds of velocity like instantaneous velocity, average velocity, uniform velocity and all, even for the acceleration we have the same kind of classification. Taking the first one, what is, let us take average acceleration, okay, average acceleration, which is represented by AVG, okay, small a subscript AVG, okay, average acceleration. Very simple. Total change in velocity by total time taken is average acceleration. Very similar to what we discussed in average velocity case, okay. Average acceleration is total change in velocity by total time taken, okay. This is what is average acceleration, very simple. So AVG, average acceleration, AVG is equal to total change in time, sorry, total change in velocity, total change in velocity by total time taken, okay. This is what is the expression for average acceleration, very easy. Now let us see what is instantaneous acceleration. So instantaneous acceleration is referred for very small interval of time at a particular instant of time, okay. Very similar to what we have discussed in the case of velocity. Instantaneous acceleration Instantaneous acceleration is very simple. It is the acceleration of the body, okay, acceleration of a body at a particular instant of time, at a particular instant of time. Okay, now when I say particular instant of time, the factor in the denominator, the change in time should be very, very, very small, right? Very, very small. So, the actual expression of acceleration is a is equal to delta v by delta t, right? When it comes to instantaneous acceleration, the time interval that I should choose should be very, very, very small, so that I get the instantaneous acceleration at particular instant of time. So, for the same expression, if I put limit delta t tends to 0, delta v by delta t, okay, then this becomes the expression for instantaneous acceleration. Instead of writing all these things, I can simply keep it as a is equal to dv by dt. Okay, differentiation of velocity with respect to time. dv by dt is the expression for instantaneous acceleration. Okay, clear? This is the expression for instantaneous acceleration. Okay, so this is about instantaneous acceleration. Now, what is uniform acceleration? Let's see that. So, very simple again, uniform acceleration. When I say uniform acceleration, if a body changes, equal velocities, okay, a body changes equal velocity in equal interval of time, okay, which means the body should be moving with constant speed, not constant speed, it can be, the body can be increasing its speed, increasing its velocity, that's fine. But the body should not be like, once it increases the speed, then becomes constant speed, then decreases the speed, comes to rest. No, this is not uniform acceleration. If a body starts increasing the speed, it must keep increasing the speed, keep increasing the speed for a long time. Then that motion is called uniform accelerated motion. Okay, uniform acceleration. The change in velocity should be same for all the intervals of time chosen. Okay, in the first interval, okay, if I take the entire motion and divide it into several intervals, then the first interval that I take, in the first interval, if the velocity is changing by say 10 meter per second to 12 meter per second, even in the next interval it should change from 12 to 14, next 14 to 16, next 16 to 18, like that. Okay, the change happening in the velocity should be same in the given intervals of time. Okay, then we call that acceleration as uniform acceleration. Okay, that's it. So that is about the three kinds of acceleration that we have. Now, the extra uh, factor that comes here, extra classification that comes here in acceleration is retardation, or which is also called deceleration. Let us see what is deceleration or retardation. Okay, what is retardation? Okay, retardation or deceleration, both are one and the same. Okay, now if, see, when I say the body is accelerating, its velocity is increasing with respect to time. When I say decelerating or retarding, then it means that the body is getting slower with respect to time, which means the speed of the body is decreasing with respect to time. Okay, not speed, velocity. Okay, so if the velocity of the body, if the velocity of the body decreases with respect to time, okay, decreases with respect to time, then it is called negative acceleration, okay, it is called negative acceleration, or it is again called as retardation, okay, it is also called as retardation, or the same factor is also called as deceleration. So this is about retardation or deceleration. Very simple. If the velocity of the body decreases with respect to time, then it is called negative acceleration or retardation or acceleration. Okay. So this is the general definition. Rate of change of velocity with respect to time is the general definition of acceleration. But when it comes to specific definition of deceleration or retardation, it is defined as if the velocity of the body decreases with respect to time, then the motion is called decelerated motion or retardation. Okay, clear? So it is also called as negative acceleration. See, in both the case, what we have is acceleration itself. In the first case, what we have is the body is increasing its velocity. Okay, velocity of the body is increasing. Then we call the motion as accelerated motion. In the second case, the body is decreasing its speed. Okay, becoming slower. In that case, we say it is decelerated motion. But for both the cases, numerically, when I say numerical value of the acceleration, for both the cases, it is taken as acceleration itself. So, for increasing speed or velocity, okay, for increasing velocity, acceleration is positive. Okay. So you sit in the car, you start the car and just leave it. I mean, you put the pedal on the accelerator and the velocity of the car starts to increase. Then it is accelerated motion, and the motion is said to have positive acceleration. Okay, the value of the acceleration that we keep is positive. Okay, and for decreasing velocity, the kind of motion is said to be decelerated motion or retardation, and the value of acceleration that we put, the numerical value of acceleration that we put, is going to be negative. Okay, so that is the difference for the numerical representation of acceleration and deceleration. When I say acceleration, it is increasing velocity. When I say deceleration, it is decreasing velocity. Okay, so that is about acceleration and deceleration. Okay, now whatever we have discussed so far includes the definition, formula, unit and dimensions and classifications of quantities which are distance, displacement, velocity, speed, acceleration, right? Now, this is about numerical discussion, the definitions and all, everything is written one. But now, if we want to represent the same quantities in a graph, then how do we do that? Okay, because when I put a graph, instead of writing a sentence, so many factors can be observed in a graph. Okay, getting the idea? What is the intention of drawing a graph? Intention of drawing a graph is to have idea about so many factors without actually writing them down in detailedly. Okay, if you have a single graph, you can analyze so many things from the graph. Okay, we'll see what and all we can analyze from the graph. So when it comes to motion in a straight line, we have two types of graph in the board syllabus to study. Okay, the first graph is, the first graph is position versus time graph. Okay, so it is position versus time graph. The graph, which is also called as PT graph, okay, which is also called as XT graph, because uh, X is the symbol that we make use to represent position in some references. So, which is also called as XT graph, okay, position versus time graph. It's also called PT graph. It is also called XT graph, okay. So, what is position versus time graph, PT graph? When we draw position of the body along, or represent position of the body along y axis, and time taken by the body along x axis, then the graph that we obtain is called PT graph or position time graph. Okay, let us see in detail about the graph now. So, as I said, we are going to put a graph with time along x axis and position of the body along y axis. Okay. Now, what if I say, what if I take a point here on the origin? It means that the body is at position 0 when the time is 0. And then if I take one more point here, okay, it means that the body is still at 0 position after a certain time. Okay, so let me name the number, put the scale. Okay, 1, 2, 3, 4, 5 units of time, normally seconds, and here position, it is 1 meter, 2 meter, 3, 4, 5. Okay. Now, see, we are still in motion in one dimension discussion. So, this is the position 0. Okay. I need to extend the graph in both the directions. Okay. -1, -2, -3, -4, -5. So, in the graph, say the body is, okay, this is what is the line which we chose while discussing in the beginning of the chapter, right? Do you remember this? The railway track that we chose, and afterwards the railway track did not have any reference, so we put the numbers 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. Okay. So now, if the body is at the origin in the beginning, okay, the body is here, or let me take the same example, like body was at somewhat like -4 meters. Okay. So the body was at this position when we started to observe the motion, which means the time has just begun. Okay. The time has just begun, and hence the body, which means the time is 0 when we first find the initial condition of the motion, and the body is at -4 meters. Okay. Here is the position -4 meters when the time is 0 seconds. Okay. The motion is just beginning. So next, say from -4 it goes to +1. Okay, from -4 it goes to +1. Now the question is, okay, fine, it goes from -4 to +1. In what time it goes from -4 to +1 is the question. Say in a time of 2 seconds, if okay, in a time of 2 seconds it goes from -4 to +1. Okay, so which means after the time t equal to 2 seconds, we find the body at 1 meter, okay, plus 1 meter, here it comes, but the time has become 2 seconds. Next, from plus 1 meter, it goes to 4 meters, okay, from plus 1 meter it goes to 4 meter. Say in what time again? Say in a time of 1 second. Okay, 1 plus 1 to plus 4 in 1 second. So it goes from plus 1 to plus 4, but in 1 second. 2 seconds has already elapsed, and now 1 more second, which means the total time taken is 3 seconds. So after 3 seconds, the body was at 4 meters. Getting the idea? Now, if I join the dots, the graph look like this. So, this is the position time graph for this motion that happened. What is the motion that happened? The motion just happened is from minus 4 to plus 1, plus 1 to plus 4. Okay, this is the motion happened. But time comes into play. From minus 4 to plus 1, it takes 2 seconds. So, the point shifts from this to this position on the graph, and from plus 1 it goes to plus 4 in 1 second. So, the point goes from here to here. So, joining the points we get a line, and this line is the position time graph for this example that we chose. Okay. So, this is how we discuss different types of position time graphs and its applications also. There are applications, uses of this PT graph. Okay. Say now you have a line starting from the origin, okay, like this. This is also a PT graph, okay, where in this PT graph the body was at rest, okay, because the body was at the position 0. Okay, the body was at position 0 when the motion just began, and afterwards from 0 the position starts to change with respect to time. Okay, so this is a simple PT graph. Now we shall take different PT graphs and analyze the different factors based on different types of PT graphs. Okay, first of all, very simple PT graph. Okay, see, position, time. Now you see, when you have a PT graph like this, okay, yeah, let me give you the factors that can be obtained using PT graph first. So I just gave you the example like this, right? So this is the PT graph that I am taking as example again. Okay, so it is 0, 1, 2 second, 3 second, 4 second, 5 second, 6. 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meter. So say I have a line like this. Okay. So if I have a line like this, then what is the uses, or what are the uses of this graph? See, when I look at this graph, I can analyze what is the instantaneous position of the graph. Exactly after 2 seconds, where was the body? Just by looking at the graph, I can say exactly after 2 seconds, the body was at 2 meter. And exactly after 4 seconds, where was the body? After 4 seconds, the body was at 4 meters. For this graph, okay. So from this graph, we can get the instantaneous position of the body, okay. And we can also get one more thing. Using the graph, using the PT graph, we can also obtain velocity. How do we get that? We need to get the slope of the graph. What is slope of the graph? See, slope of the graph is nothing but you choose certain part of the graph, okay, certain part of the graph which should be linear, okay. The chosen part of the graph, this is the graph which starts from here, ends at here. You can choose any part of the graph, this much, this much, this much, or this much, all of this much, okay. You can choose any part of the graph, but the part that we choose must be a straight line. There should be no variation, okay. It should not be varying again. So let me choose this part. Yes, I can choose any part because it's completely straight line. So if I take this part from one point here and the other point here, this much of the graph is taken. So when I take this much of the graph, how do we now using this, how do we get the slope? Okay, as I said, uh, after considering certain part of the graph which is a straight line, we will draw a right angle triangle. Okay, we will draw a right angle triangle such that the chosen part of the graph becomes the hypotenuse of the triangle. Okay, how do we get slope? First, we will consider certain part which is a straight line, and we will construct a right angle triangle such that the chosen part of the graph becomes hypotenuse of the right angle triangle. Okay. So now what is this? This is second position. Okay. Position can be either taken as P or as X, both are fine. Let me take this as X2. Okay, second position as X2. Okay. And what is this? So this is actually x2, right? And this is x1, initial position. Here the body was at 2 meters and now it is at 4 meters. X2, this is x1. And similarly, when it comes to x-axis time, at this point, the time is t1. Now the final time is t2, and at this point, the time is t1. Okay. So this length what we have here is x2 minus x1, right? Isn't it? Final position minus initial position, which is nothing but delta x. What is delta? Change in position. This change in position itself is x2 minus x1, final position minus initial position. Similarly, when it comes to time, final time minus initial time, which is delta t. So, slope of the graph from this is delta x by delta t. Okay. Slope is always the change in the value of y axis, change in the value of y coordinate, and by the change in the value of x coordinate quantity. Okay. In the y axis we have position, so that comes first in the numerator divided by the x axis quantity, which is time, and that comes in the denominator. Okay. This is what is slope. For any graph, slope is change in y axis value by change in x axis value. How do we get that? We need to choose certain part of the graph which is straight, and then we should draw a right angle triangle in such a way that the chosen part of the graph becomes the hypotenuse of the triangle. Then we take change in the factor or change in quantity which is there in the y axis first. We take that and put that here in the numerator, and we take the quantity or change in quantity which is there in the x axis, and we take that and put that in the denominator, and hence we have slope. Okay. So from formula, what is delta x by delta t? Yes, it is slope for any graph. Okay. Slope for any graph is delta y by delta x, change in the value of y axis quantity by change in the value of x axis quantity, and this is the slope for this graph. Now what is this delta x by delta t? You have just we have just discussed about it, right? Delta x by delta t, rate of change of displacement, rate of change of position, both are same, which is velocity. Okay. So slope of a PT graph gives us velocity. Okay. Slope of a PT graph gives us velocity. So we can write V is equal to delta x by delta t. Keep this in mind, very important. Okay. Velocity is nothing but slope of PT graph when it comes to position analyzing the graphs. Okay. So not only the instantaneous positions, but also the velocity of the body can be taken or can be uh, calculated using the PT graph given. Okay. So both the things can be done, both velocity and instantaneous position can be analyzed. Okay, now we shall take different PT graphs and analyze them. Different PT graphs. See, the first graph that I'll choose is a straight line, okay, a straight line which is parallel to x-axis, okay, a straight line which is parallel to x-axis. This line can be here, 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 or on t itself, or on x-axis itself, or it can be beneath or under the x-axis here. It can be anywhere, but a straight line parallel to x-axis. If you have such a graph, then what is happening here? See, if you observe carefully, time is changing with the graph because the points can be considered here. Now, as you can see, when the point changes from this point to this point, the time has changed from 0 to 1 second. Then from here to here 1 to 2, from here to here 2 to 3, from here to here 3 to 4. So time is changing. Okay. What about the position? Position of the body even after the change of point is same. At this point position is 1. At this point 1 again, 1 again, 1, 1, 1. So no change in position, but the time is changing. Which means when do you expect this kind of situation? When the body is situated at a particular point, when the body is not moving at all, when the body is in rest, then the time will keep on changing, but the position will remain the same. So the body is fixed at a point, it is not at all moving. Okay, so this is a graph in which the body is in rest. In other words, we can say velocity of the body is 0, right? When the velocity is 0, the body stays in rest. In other words, when the body is in rest, velocity of the body is 0, right? So that is about the first PT graph, which is a straight line parallel to x-axis, which means the body is in rest and velocity is 0. Okay, fine. Now moving ahead, the second PT graph PT. The second PT graph is a straight line passing through the origin. Okay, not necessarily passing through the origin, it can be starting from here, but it should be a straight line like this. Okay, so now what is happening here? So when the points are shifting, time is changing obviously, and along with time position is also changing, right? So which means that the body is moving. Okay, but now as you can see, slope of the graph at every point on the graph, okay, slope of the graph at every point on the graph is same. See, slope can be generally, or just to analyze the slope I can make use of this pen. Okay, say when I have a graph like this, we can say this has certain slope. Now if I have one more graph like this, now I can say the second graph, this one has more slope compared to this. Okay, so you can calculate it. You just construct a right angle triangle and put delta y by delta x. You will get to know that this has less slope compared to this. But now to analyze, I can assume that more the deviation from the x-axis, okay, more the deviation from the x-axis, more the slope is. Okay, so this one has less slope. So this nib has deviated much more angle of deviation, so slope is more. So for a PT graph, when the slope is more or less, it means that velocity is more or less, because slope itself is the velocity of PT graph. What about the slope for this graph? Slope for this graph is 0. when the graph is parallel to x-axis, at every point it is parallel to x-axis, and hence the velocity is 0 at every point that we choose. Okay, 0, 0, 0, 0. If I get a slope like this, then it is not 0. Okay, then velocity is not 0, it is changing. Now let me take this. Here, is the slope 0? No, it is not. It is deviated by some value. But the deviation is not changing. Okay, the nib is not changing by any angle when it moves ahead in the graph. So since the deviation is not changing, slope at this point is equal to slope at this point is equal to slope at this point is equal to slope at this point, and hence the slope for the entire graph is same. So velocity for the entire motion is same. So this graph shows that we have the body moving with same velocity or constant velocity. Okay, same is also fine, constant is also, it's not changing. Body moving with constant velocity. Velocity is not changing. Okay, a straight line like this, which is not parallel to x-axis, gives us the idea that a body is moving with constant velocity, which is not changing. Okay, the velocity is not changing. Now, moving ahead, the next graph that we take is as follows. Next PT graph. So now the graph is like this. When I have a graph like this, what is happening to the velocity, or what is happening to position? Yes, obviously position is changing with respect to time. So the body is moving. Okay, but what is happening to the velocity? See, here at this point we have this much of deviation. But when I take the pen and keep it here, the deviation increase from this to this, right? Moving ahead, increasing. The deviation is increasing. Okay, you observe. Here it is like this, and here it is like this. So the deviation has increased like this, which means the slope has increased when with the graph. So here the slope was less. As we move ahead, slope is more, which means initially the velocity was less, and when the graph moves ahead, the velocity increases. Following? So this is the motion moving, where the body is moving with increasing velocity. Okay, the body is moving with increasing velocity. Clear? Very easy. Now, the next example, next graph is as follows: PT. Okay, this time, so this is how the graph is. Now, what is happening to the slope? At this point, slope is very much, see, the deviation is very much. Okay. Now, as and when it moves ahead on the graph, the slope decreases, right? You take this position, the slope is less because the deviation is less, this much deviation. You take this position, deviation is this much. So, more slope to less slope, more velocity to less velocity, which means the body is moving with decreasing velocity, right? So this is the PT graph where the body is moving with decreasing velocity. Okay, we'll take few more graphs, analyze them in the next session, and afterwards we'll go for the other kind of graph. Just go through them, these are very important. Okay, thank you. Yeah, one more thing that I want to put here is what is happening to the acceleration in each case. In the first case, the velocity is not changing. Whenever the velocity is not changing, we say acceleration is 0. Velocity is obviously 0, 0, 0, 0, 0. So every time the velocity is 0, which means acceleration is 0. Okay. Let me take the second case. In the second case, slope is constant, which means velocity is constant, say 5 meter per second fixed. 5 meter per second, 5 meter per second, 5 meter per second, 5 meter per second, same velocity. But now, what is the change in velocity? Change in velocity is 0 because the body is moving with same velocity. Since there is no change happening in the velocity, acceleration is again 0 because acceleration can be only seen when the body is either increasing its velocity or decreasing its velocity. Here the velocity is same. When the velocity is same or constant, acceleration is 0. What about this? Here the velocity is changing. Yes, it is changing. Slope is changing. But what kind of change it is? Whether it is either it is increasing or decreasing. So the change that we see here is increasing velocity. When the velocity is increasing like this, then the change in velocity is positive because the final velocity will be more than initial velocity, right? Here at this point it is say 10 meter per second, before 2 seconds it is 5 meter per second. So velocity is increasing with respect to time. Final velocity is more than initial velocity, and when the body is increasing its speed, you say the body is accelerating or positive acceleration is happening. Okay, so for this increasing velocity, acceleration is positive. Okay, and for this decreasing velocity, okay, initially it had very good speed, but gradually the speed decreased. What is this case? This case is retardation, isn't it? The velocity is decreasing for the body. When the velocity decreases, like when does it happen? When it happens when the brakes are applied, isn't it? When the brakes are applied, the speed decreases or velocity decreases. When that is the case, it is retardation, or in such case acceleration is negative. Okay, so acceleration is negative for this. Clear? Okay, these are the 4 graphs, and what is happening to velocity and acceleration in each graph is what we have discussed here.